The Physics of Interstellar Travel, Chapter 6, Ion Engines. In a chemical thermal rocket, the fuel energy and the propellant mass come from the same source. For example, hydrogen is burned in oxygen to release energy that then propels the product of this reaction, water vapour. In an ion engine, the fuel and the propellant are separate. The principle of an ion engine is simple. A gas is first ionized into its constituent ions and electrons. The much more massive ions, shown here, are then accelerated by an electric field out of the back of the engine. By conservation of momentum, this accelerates the rocket in the opposite direction. In a thermal rocket, the mechanism for the momentum transfer is the collisions of the hot gas particles with the walls of the combustion chamber. In an ion engine, it is the electric field attached to the rocket pushing on the ions, equivalently the ions pushing on the field, that provides the momentum transfer. Although when you think about it, the interactions of hot gas particles with the walls of the combustion chamber is also governed by electromagnetic fields. The electrical energy required to ionize the gas and then accelerate the ions could come from any source, such as solar panels, or a nuclear reactor that drives a turbine to generate electricity. In all cases, the source of energy and the source of the propellant mass are separate. Xenon is often used as the propellant gas because it has a relatively low ionization potential, is non-toxic, and it can be liquefied and stored for long periods. An actual ion engine is of course more complex, and even this sketch here does not show all the details. But I'll draw your attention to a few things. Electrons are emitted from the cathode on the left by thermionic emission. These electrons then collide with the xenon gas atoms and ionize them. The xenon ions are then accelerated by the strong electric potential towards the right and through the grid out of the engine. To prevent the spacecraft from becoming increasingly negative charged with time, electrons are injected into the exiting beam in order to neutralize it and keep the spacecraft neutral too. The ion beam has a very low density, and to maintain the plasma within the engine, it has to be operated in the near vacuum of space. The mass flow rate from the engine is anyway very low, so ion engines cannot be used to launch a spacecraft from a planet's surface, where a large thrust is required to overcome gravity to even get off the ground. Ion engines are instead used for accelerating once a spacecraft is in space and for maneuvering. Here we see a photograph of the N-Star ion engine, which was flown on both the Deep Space One and Dawn missions, both of which visited minor bodies in the solar system. When used on the Dawn spacecraft, N-Star delivered an effective exhaust velocity of 30 kilometers per second and a thrust of up to 90 millinewtons, which together imply a mass flow rate of 3 times 10 to the minus 6 kilograms per second. Now, this exhaust velocity of 30 kilometers per second is much larger than that achieved with chemical rockets, which we saw in an earlier chapter is limited to around 4.5 kilometers per second. But the mass flow rate with an ion engine is tiny. Here it is just 11 grams per hour, and this is why the thrust is so small. In contrast, the liquid hydrogen-powered Vulcain engine of the Ariane 6 rocket delivers a thrust of 1.4 meganewtons at launch, which is 16 million times as much as the thrust of this ion engine. Dawn had a dry mass of 747 kilograms. The dry mass is the mass without any fuel or propellant, and it carried an additional 425 kilograms of xenon propellant for the ion engine. Now, whereas most chemical rockets have many times more propellant mass than dry mass, we see that Dawn has actually less propellant mass than dry mass. But on account of the large effective exhaust velocity, this was enough to allow the spacecraft to achieve a total delta V of 11.5 kilometers per second over the mission lifetime. Actually, if you do a calculation using the rocket equation and the above masses, you'll see that you get a larger value. The discrepancy can be explained partly because Dawn also had a small chemical engine and chemical fuel. This 11.5 kilometers per second delta V would take a long time to achieve, however, because the acceleration is so small. If the engine is fired continuously for 10 days, the spacecraft's speed changes only by 64 meters per second. Over this time, it exhausts just 2.5 kilograms of propellant, and at this rate, the engine could be run for 4.5 years. In reality, the N-Star engine has a variable exhaust velocity and variable thrust and operated for nearly 6 years. To power the iron engine, Dawn used a very large array of solar panels, 36.4 square meters to be precise. This provided more than 10 kilowatts of power when the spacecraft was at the Earth, which is 1 astronomical unit from the Sun, but 9 times less when the spacecraft got to the asteroid Ceres at 3 astronomical units. So this was just a very brief introduction to iron engines. In the chapter, I provide some calculations for the exhaust velocity, thrust, and power. I also briefly summarize a few other types of iron engine, such as the Hall thruster.